Hello and welcome to this presentation on the oscillation of a pendulum. This is being made primarily for my students at the Dakar American University of Science and Technology for a course in mechanical vibrations. A pendulum is a very simple device, as we'll see. It only has one moving part, but actually there are a lot of principles that need to be mastered related to oscillating systems, which of course is what vibrations is about, that are illustrated in the example of a simple pendulum. So a simple pendulum is, like I said, a device with one moving part. We can see that moving part over here. The pendulum pivots about a point, hangs from that point, and turns about that point. And it has a rod that's one piece of it, and then attached at the bottom is a mass, M. So the rod has length L, the mass has mass M, and all of this is happening in a gravitational field with strength G. So the pendulum swings back and forth around the pivot point. Now what we're after in modeling this system is we want the time history of the pendulum's motion. And what that means, the parameter that we're looking at here is theta as a function of time. And I've defined theta to be the counterclockwise rotation about the pivot point. Theta will be in that direction. Theta dot, which I haven't shown here, which is the angular speed of the pendulum, also in that direction. And then theta double dot, which is the acceleration of the pendulum, all will be in the counterclockwise direction. Now on the left, we show the pendulum deflected at the top of its swing. So at this point in time, the pendulum is not moving, and it has moved up from its lowest position, which is shown on the right, and stopped. So it has no energy of motion, it has no kinetic energy, it's just stopped, and it has at that point in time all of its energy as gravitational potential energy. On the right, we show the pendulum in its vertical position. So it's swung down from the highest position, and it's going through the vertical position here on the picture on the right. It's at its lowest point. Now you can set your reference point for gravitational potential energy to wherever you want it, but most commonly that's set to be the lowest point that the mass passes through in the system. So at this point in time, or at this point at the position of its motion, the mass is at its lowest point, and so all of its gravitational energy, which it had in the drawing on the left, has been converted into energy of motion, or kinetic energy. And I symbolize that as energy of velocity, which is kinetic energy. Also, since there's no energy being put into this system or taken out of this system, we're assuming a frictionless pivot. The mass is moving at its fastest speed where it has its maximum kinetic energy. And it has its maximum kinetic energy at the place where it has its minimum gravitational potential energy. Now, the system does have the same amount of energy on the left as it does on the right. It's just two different types of energy. On the left, it's completely gravitational potential energy. On the right, it's completely the energy of motion, or kinetic energy. But since there's no energy entering or leaving the system, the energy state, the amount of energy the system has, is the same when the pendulum bob has rotated up and stopped, as it is when it has fallen down through its lowest point and is moving at its fastest speed. And we will use that fact in our analysis. Okay, I'm going to stop right here and start up with part 2 in a minute.